the tables, I can do what is called one-hot implementation. One-hot implementation means this. Correspond one flip-flop to every state that you have. So 4 states, 4 flip-flops. Wire the flip-flops together with their clocks. And then for every flip-flop, if you are in the state A, it's as if this signal is 1. If you are in this state, as if this line is 1. As if these lines are 1. So when you are in state A and your x is 0, you are coming back to A. And therefore you are saying, if I am in state A and my x is 0, I am coming back to this state. On the other hand, if I am in state A and my x is 1, I am going into state B. When you are in B, if you are in B, that means ANDed with the B output. If your B is 1, if your x is 1, then you are coming back to state B, and therefore you are bringing a line back here. Since there is already a line into the state B, there is an OR there. And if this line is 0, you are going into state C, and therefore you are going into state C. Okay, so what it is you replace the circles with the boxes, with flip-flops, and you would replace the edges with AND gates. Okay, a zero input will give you a bar on the end, the side. A 1 input will give you just a straight through line from the input to the AND gate. This implementation is very easy. You don't need any Carnot maps, you don't need any transition tables or anything, but you use more flip-flops but fewer logic. Okay, fewer logic gates. This is that implementation drawn nicely, and I'm using rising edge flip-flops, and notice that, for example, in state B, there are 3 inputs going into state B. 1 from itself, 1 from A, 1 from D. Okay? 1 from itself is this one over here. 1 from A, and 1 from state D. Okay? And therefore I have an OR gate here with 3 inputs. For state C, I have 2 edges, and therefore I have an OR gate with 2 inputs, this one over here. For the state D, I only have, oops, not this one. For state D, I only have 1 edge going into it, and therefore I have no need for an OR gate. But if I did have an OR gate, it would just be a 1 input OR gate. Where does my output come from? I'm sorry, I keep going back to that. Where does my output come from? Well, my output when I'm in state D, my output is 1 if my input is 1. And therefore, if I'm in state D, if my input is 1, this is my input. See? If I'm in state D, if my input is 1, my output is 1. And therefore, this AND gate becomes the output of my circuit. And this is called one-hot implementation. Why one-hot? Because the same way that at any point in time you're only in one of these states, or one of these states is active, in this diagram also, at any point in time only one flip-flop output is active. All other flip-flop outputs are 0, and therefore you have to start with 1 0 0 0, and then the next state becomes 0 1 0 0, the next state 0 0 1 0. In a way, what you have is your state A is 1 0 0 0, your state B is 0 1 0 0, your state C is 0 0 1 0, your state D assignment is 0 0 0 1. This is also called one-hot assignment. Okay, much less logic, but then more flip-flops, but then much easier to implement than that. But then requirement is that you have to have some kind of resetting so that you start with 1 on the first flip-flop and 0 on the rest of the flip-flops. Otherwise the circuit is not going to move if they're all set to all zeros. So for resetting, I'm going to use green here. I'm assuming this has a set and a reset, a set and a reset, a set and a reset, a set and a reset. I bring in an external line to set the first one. That same line, now the reset is going to be 0. That means I'm not activating it. On the other hand, the set is going to be 0, not activating it, not activating it. And then this same line goes into the reset of this, like that, goes into the reset of this, goes into the reset of this. Okay, and so when you put a 1 here on this set input of the first one, it will put a 1 into the first one and then 0 into the rest of them. That means it starts it in state A, and this becomes your reset. Notice that the flip-flop symbol I have used is using asynchronous active high set and reset inputs. Okay, and this is rising edge clock. And this is called one-hot realization. I could do this for the Moore machine as well, and this would require 5 flip-flops. All right. Another state machine I'm showing you is a counter. Okay. I have 4 states here, states A, B, C, and D. Okay, well, this is really no different than the state machines I've shown you before. Okay, I have 2 outputs for each state. That's one difference. And in state A, I have 0, 0 output. In state B, 0, 1 output. In state C, 1, 0 output. In state D, 1, 1 output. If I'm in state A and then an external input is 1, I call my external input UD, which you will know in a second, or UD bar. If UD is 1, you will count up from 0, 0 to 0, 1, from 0, 1 to 1, 0, from 1, 0 to 1, 1, rolls over from 1, 1 back to 0 if UD bar is 1. So UD bar is count up, and then if you have a count down, UD bar is count up, UD bar is 0, then it's counting down. Okay, meaning that if you are in A, counting down will roll back over to 1, 1, 1, 1 to 1, 0, 1, 0 to 0, 1, and 0, 1 back to 0, 0. Counting up and counting down. I'm calling this circuit a modulo 4 binary. Why binary? Because it is counting binary numbers. Up, down, counter. Why modulo 4? Because it has 4 states. Why up, down? Because it has a control input that either counts up or counts down. Implementation of it is easy, the same way we did before, except that now, since these are the outputs, I'm going to set the state variable, state assignment for A as 0, 0, for B as 0, 1, for C as 1, 0, for D as 1, 1, so that the outputs of the states will be the same as the circuit outputs. Yeah, I didn't call this UD bar here so that you don't get that confused with the Boolean expression of anything. I'm only using it as a name. So maybe we should use this UD bar. UD bar. So if UD bar is 0, I'm extracting these two tables for actually for y1 and y0, but then I decide I want to do d flip-flop, and therefore these tables become d1 and d0. I have skipped the state table, the transition table, the excitation table that I did before. Remember we did this? We started with the state diagram, then the state table, then the state assignment, then the transition table, then deciding the D flip-flop, the excitation table, and finally Carnot maps. I have skipped in this counter example all of those states and go directly from this state diagram to my excitation tables for D1 and D0. Mapping all of these, this D1 becomes a XNOR of the three inputs, and D0 becomes C0. Okay, I'm sorry, C0 bar, and therefore this is my counter. This is a 2-bit counter, 2-bit up-down binary counter. Okay, what if I want to have a counter that counts up, counts down, and loads a 0, does a parallel loading. Parallel loading means that at one point I decide that I want to have some data from outside loaded into the counter. Okay, or parallel load the counter. I build a counter like this. M1, M0. If it is 0, okay. If it is 0, do nothing. If it's a 1, if it's a 1, load with 0. If it is a okay, 2, up count, and if it is a 3, parallel load, meaning put P1, P0 into the counter. Well, what do I need? I need a multiplexer that can select one of these 4 inputs. For 0, 0, I'm gonna do colors again. No, not yellow. It's not gonna show well. Okay. If this is 0, 0, I'm gonna get the 0 here. I'm gonna get the 0 here. I'm gonna get the 0 here and 0 here, and therefore this will go back to itself. This will go back to itself. Actually, doing nothing means don't touch the count. It means that it's feeding back to itself, keeping the old count. So the doing nothing is implemented. Doing nothing is not exactly doing nothing. It does something. It puts itself back into it. Load with 0, 0. Well, if it is 0, 1, I'm putting a 0 here, a 0 here, and therefore I'm loading it with 0, 0. If it is 1 0. Okay, this input is going to be activated. This input and this input, the rightmost or the least significant bit is going to be complemented. See, because 0 0 going up becomes 0 1, 0 1 going up becomes 1 0, and therefore this bit is always complemented. And then the 1 0 becomes 1 1, so it's complemented. And the leftmost bit is always the XOR of the two bits. For example, 0 0 XOR of them is 0, and therefore this is it. 0 1 XOR of it is 1, and then this is this, and therefore XOR becomes the leftmost bit input. And then finally, if my input is 3, then this is going to be selected, and therefore I'm putting the parallel load into this counter. In addition to everything that I have shown about this counter, which has 4 modes of doing nothing, resetting to 0, counting up, and doing parallel load, there is something else about this counter, and that is the carry out concept that is very important. Carry out of a counter means this. If my counter reaches its final count, let's talk about a 4-bit counter. Okay, 1, 2, 3, 4-bit counter. It has a carry in and it has a carry out. If my counter reaches 1, 1, 1, 1, and also if my carry in is 1, my carry out becomes 1. What it means is my carry out is the AND function of carry in and the 4 flip-flop outputs. Okay, so if this is a counter with 4 flip-flops, I need a little bit more space here. This is a counter with 4 flip-flops. This is carry out. Okay. Carry in ended with the 4 flip-flops. Carry in ended with the 2 flip-flops in this case here. Alright, something else I have done here, carry in is also ended with M1, M0. It means that if carry in is 0, I'm not counting up, I'm not resetting, I just use my carry in as an enable as well. That means if carry in is 0, I will only be in mode 0. Mode 0, remember what mode 0 is, means that the output feeds back to this input. Alright, so why do we talk about counters? Well, we talk about counters because we have already done the state machines, we have built the state machines, and we have built Mealy machine, Moore machine, but then we are talking about more abstract packages. Abstract packages for sequential circuits are counters, shift registers, and perhaps a memory file or something like that. And what I have shown you here is an up counter, and what I have shown you here is an up-down counter that as a package, a 4-bit one, an 8-bit one, a 2-bit one, can be used for more abstract designs. The same way I talked about comparator at the very end of the combinational circuits. Now I'm talking about a counter as an abstract sequential component. Another abstract sequential component is a shift register. A shift register works like this. You have 4 flip-flops here. If you have 0, 0, 0, If you have 0, 0, 0, 0 on these outputs, and your serial in is 1, you give it 1 clock. The 0 on the right hand side will go away. Gone. This 0 will go here. This 0 will go here. This 0 will go here. And this 1 will go here. Okay. The next clock let's assume serial in is still a 1. This 0 will go here. Okay, this 0 will go here. This 1 will go here. And this 1 will go here. The next clock, this 0 will go here. This 1 will go here. This 1 will go here. And this 1 will go here. Okay? Let's do one more clock. And let's say in this clock this became 0. This 1 will go here. This 1 will go here. This 1 will go here. And now I have a 0 that would go here. What is really happening is the data is shifted one place to the right. And this is a 4-bit shift register, right shifter. It has a serial in. It has parallel outputs. The same way I can have a counter that counts up, counts down, has a parallel input, has a the resetting, has a do nothing feature and all that. I can also have a shift register that can do all of this. Right shift with serial in from the left, left shift with serial in from the right, parallel input, do nothing, resetting this, this, and that. Okay, and a certain shift register with M1, M0, 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 is do nothing. 0, 1 is right shift. 1, 0 is left shift. 1, 1 is parallel loading. Okay, and then again, the same way with the counter. This can very easily be implemented by one flip-flop having a multiplexer on the left-hand side, selecting one of the inputs either from the left, from the right, or from the from itself, or from the outside. All right, this is a shift register, and we have covered what we wanted to cover about sequential circuits. We talked about the state machines, counters, and shift registers. Now, you have learned the basics of counters, but then you can have all types of counters. Instead of binary, you can have a counter that counts random numbers instead of a 2-bit counter, 4-bit counter, 16-bit counter, and so on. Shift registers, you can have a shift register that rotates, a shift register that shifts right, left, a shift register that has some logic, and perhaps something like this with some maybe exclusive ORs, and these are better with some feedback. Okay, and this is again the shift register with some feedback. This is called an LFSR, linear feedback shift register. All right, these become the components of higher level designs.